Welcome back, everybody, and welcome to the first video that's going to be in the DIY section. And as you can tell by my nice pink sheet of paper, we're going to talk about power. So the goal is going to be to do like just a really generic overview of how the power is distributed on a miner, what some of the troubleshooting steps you can do, what that means, that kind of stuff. I'm going to try to keep that generic, so not to go into like model specifics. There's definitely some fairly major differences between what I would say are the more modern or newer models, let's say from like 17 and above, or even maybe like 15-ish. No, I would say 17 and above, and anything before that. There's some slight tweaks that have happened. Okay, so first of all, we gotta do a quick recap on something called a voltage divider. So you may already know what that is, you may not. If you don't, then keep listening, and if you do, then sorry. You gotta start somewhere, I feel, right? So let's say we have 5 resistors connected in series. Okay, so we got 5, and that we put a certain voltage at the extremities of that chain. Let's call it 10 volts from there to there, and we're gonna assume that each of those resistors is the exact same value. I'm gonna call R, just like any value, really, doesn't matter. Yeah, so these 5 are all exactly the same. We know that for each of those, if we look at just this first resistor in isolation, so we know that this side is going to be more positive because it's on the positive side. This side is going to be more negative. If we look at just that second resistor, then same thing, this is going to be the positive side, negative, positive, negative, positive, negative, positive, negative. So yeah, so you can measure like the voltage across or at the end of each of those resistors separately, right? And that voltage is going to be equal to your total supply voltage, which in our case is 10 volts, divided by the number of resistors that we have in series, which in this example is 5. So it's going to mean that it's 2 volts. And again, that only works with those resistors being like exactly the same value. You know, in a best case scenario, in an ideal world, all the ASICs would have like the exact same internal resistance, but because of like manufacturing processes and variation in silicon, then it's just never the case, right? Okay, so that's a quick recap on what a voltage divider is. So based on that, if we had 10 volts at the ends here, if those 5 were exactly the same resistors, the same value, you can measure 2 volts here, 2 volts here, 2 volts here, 2 volts here, and 2 volts here for a total of 10 volts. Common sense, right? All right. Now imagine that instead of resistors, we have ASICs, as I kind of alluded to just now. So there's one ASIC, here's another ASIC. And we're gonna say, for example, that we have a chain of 15 in line, right? So that would be like maybe like an S17 plus that has 15 domains. So that's 5, just keeps going for a while, and then let's call this 14 and 15. So 1, 2, 3, 4, 5, ... 14, 15. So for the purpose of this example, we're going to say negative here and positive here. Okay, so total voltage, again, assuming that all those are the same internal resistance, is again the same thing. It's going to be total voltage, board voltage, which I think in the manual they want you to calculate with nominal voltage of 14 volts divided by the number of domains that we have, which is 15. And this is 1.6 volts exactly, I think. So what does that represent, 1.6 volt? Well, it's the voltage at the edge of any one domain, right? So ultimately it's what we call our domain voltage. right? Makes sense. So this is where that 1.6, or I think it's like 1.5 for a 17 Pro, and you know, depending what value you calculate as the main voltage, that changes obviously, but that's basically for anything that has a BM1397 chip, it should always be around 1.5 because that's the working voltage of that chip, right? And so for any one chip, so if we look at our chip number 5 here, whether you have a real ground on one side and a 1.5 volt on this side, or if you have, you know, in this case, a certain voltage X and on this side X plus 1.5 volts, then the chip doesn't matter. The chip doesn't care. So the chip only sees a 1.5 volt difference between those two. So if that chip is in the middle of the chain here, it sees 1.5 volts. If it's like right at the beginning here, it sees 1.5 volts. If it's at the very end, it also sees 1.5 volts. So it should be happy. And of course, I should mention that. Just grab another piece of paper. So I did have. Here's back our 5 ... 14, 15, and here's our, let's go positive now, negative, doesn't matter. So each of those is actually a whole domain, right? So you would have, again, in the case of an F17 Plus, 5 chips that are connected in parallel using the same point. So the voltage here is still going to be the same, having your 1.5 volts or 1.6 in the case of the S17 Plus. But then again, this voltage is seen by those 5 chips. And what we got to know and what we got to remember is that if we have one of the chips that is internally shorted between its positive and negative pad, right? So, you know, when you remove the chip, you have like a big pad as the negative pad, and then you have like a smaller rectangular pad on top. That's your positive. So negative, positive. So if through the chip those two get shorted, then that effectively shorts your whole domain. So your whole domain, all those chips, won't have that 1.6 volt as the main supply that they need to get working. So again, something to keep in mind. Now if we look at an actual board, and just keep that close by. Let me zoom you guys right in. Alright, so S17 Plus boards. This is domain number 1 under my pen. This is domain number 2. This is domain number 3, so on and so forth, going that way. And we know that when we measure the domain voltage, we measure from the top of the chips, right? Or the top of the heat sinks. Well, the top of the heat sinks are electrically connected to the top of the chips, and hopefully the top of the chips are connected through the chip to their respective grounds. And there's some subtleties there, but let's not get into that as part of this video. Let's just assume that they're directly connected to ground. So if on this side, this is domain number 1, this is the start of the series chain that's going, you know, that way. So this is the most negative part that's directly connected to my main board negative post. And then as far as voltage, it just keeps getting higher and higher as I move up. You know, much like from here, it was getting higher and higher as I was moving this way, right? So starting from 0, the main negative, all the way to the main positive of the board, which is like, you know, let's say call it 24 volts for a S17 Plus. So when I measure voltage domain from the top of number 3 to the top of number 2, domain 3, domain 2, it's really equivalent to measuring what I like to think is a better way to measure it, or to think about it, to measure from this, which is the ground of this chip. This is the ground, and this, the top of the chip in number 2 domain, the ground of this chip is really this trace right here. So measuring this is really the equivalent of measuring this. And when we measure domain voltage like this, if it's the equivalent of measuring from trace to trace like this, then you're really measuring the voltage difference across this chip or this whole domain, because they're connected in parallel, right? So if I don't have a voltage domain value, or if it's zero basically, then that means that I'm gonna have the same thing measuring like this, and it means ultimately that something in that domain, this second domain, is not happy. So any of the 5 chips in this second domain could be shorted internally, which means I would not have any voltage difference when I measure it like that, which means that I would not have any voltage difference when I measure it like that, right? And so this is just something to keep in mind. So when you do some troubleshooting and then you find that your chain is broken at the start of a domain, whether it's from the top or the bottom of the board, quote unquote, depending on what you call top or bottom, but basically, there we go. So as you know, so we start number 1 here and we snake back and forth. So if my chain stops, let's say this chip is good, like I can get this chip to get detected, and I cannot get that next chip to get detected. Or the same thing, if it's at this end, if I can get this chip to get detected, but I cannot get that next one over here to get detected. This is one end of the domain in both of those cases. And so one thing to keep in mind is that, well, you gotta check your power, right? So, and checking domain voltage really through the top of the heat sinks is, 80% of the time a good thing to, or a good way to do it. But there are some cases that I've seen where the top of the chips doesn't actually, or is not connected electrically anymore to the actual ground of that chip. So something to keep in mind, and the chip still works fine. And so what you can do when that happens is to, if I measure from heatsink to heatsink here, and I don't have a result, or I got some weird floating value, then I can try a different set of heatsink, or just like any combination. Like all of those in theory would be connected to the same ground, because all the chips on the same domain have the same ground, because they're all in parallel. So I can try different heatsinks, and if everything fails, then you can squeeze in there, maybe not through the bottom or through the middle of the board there, but probably on this side. You can see the traces are a bit more accessible, so you could come in at an angle and fairly easily touch the traces and measure the domain voltage like that. So something to keep in mind. And so there are other aspects to power distribution. So a lot of people, especially when they start, they think that the chip is powered by pin 1516 and 1718, which is the 1.8 and the 0.8 volt, but that's just not true. So those voltages are just secondary voltages, secondary power supplies that just enable some of the functionality in the chip. The main power, the main driver is really through those 3 big traces that do the voltage dividing and carry the big power through from one domain to the next. Okay, so I realized that I talked a lot about the power distribution between the chips and between the domain, but I didn't really talk about like the higher level power distribution from the board. So again, this is a little bit model dependent, but it's still pretty similar across the board. All I'm gonna say is that you have your 4 Mosfets here, right? And so these Mosfets take your main positive as an input, and then get turned on. Their gate gets turned on by your PIC, and whenever that happens, then they let the power go through, and then they're the ones that generate the main voltage that ultimately gets applied to this whole series connection of domains. So let me get a pointing apparatus again. Take this guy. All right, so hard to see maybe right now, but so this is the output, right? These 3 pins. So you got your gate, which is the pin number 4 on this side, but these 3 other pins are actually the output of the Mosfet. And if you were able to see like the copper traces, it's a little bit harder to see on video, but you see here this line. So this lighter green is where the copper is, and it's basically this whole area is all the same piece of copper. So my point is that this output is really what feeds the main positive, right? This is where the end of our chain of domain, where the chain finishes, and this is the most positive end, which is fed directly through the MOSFETs. And then I just happen to have a chip removed here, but as you can see, so again, oh yeah, and here usually there's like a metal fence on those boards, right? But I removed it for to access this chip and make my life better. But so that's a good example. And this is the underneath of the chip. And so you see this again, this big copper piece, which is the most positive supply, and this is where our traces begin. And so this positive pad is directly connected to these traces. I don't have my multimeter on right now, but trust me 100% that this is a complete short. This is all connected together. And the same thing between this main negative pad and the traces on this side. So this is again directly connected. And so this is how the chain gets, or the voltage gets distributed through the chip. You have like the positive pad of the chip that gets connected to the most positive side, and then the negative pad gets connected to the more negative side. And this goes on in series from domain to domain, and this is how it gets distributed. So that is that. Hopefully that was a bit of supplemental information that I just realized that I could show you, and on this same board that I have right now. So let's talk a little bit more about boost circuit and what it does. So the boost circuit isn't used for the main power of the chips. It is not used for that. As we saw, the main power is solely done through voltage dividing. But we also know that each domain needs a 1.8 volt and a 0.8 volt. And those are regulated down from another voltage through those regulators that are on the back, right? So these guys, every domain has 2 chip, one 0.8 or one 1.8 volt that takes basically a supply voltage of a certain value, regulates that down to 1.8 volt, and then that 1.8 volt goes and feed the chips. And also on top of that is used as an input by that second LDO, which regulates it down a second time from 1.8 to 0.8 volt. And then that 0.8 also goes and feeds the chips. So this is how those two supplemental power are generated. But in order to generate 1.5 volts or 1.8 volts, from for each domain, then that 1.8 volts needs to be relative to that domain's ground, if that makes sense, right? So if I'm in the first domain, there's going to be 1.8 volt relative to the first domain ground, which is the main board ground. If I'm up to like the 6th domain, then that chip or those chips need to see 1.8 volt relative to their own ground. So if they need to see, or if they end up seeing 1.8 volt relative to that first domain, then that's, for them, that's a negative value, right? That's lower in voltage than even their ground. So that wouldn't make any sense. So all that to say that each domain needs to have some sort of voltage used as input to those LDOs in order for them to generate 1.8 volt. And rule of thumb, usually to regulate, you need at least half a volt higher, right, for some overhead and for some of the chip that's going to do the actual regulating. So if I were to do 1.8 volt, then I would need at least probably 2.3 volts. And this is like bare minimum. So you probably like double that, really. Like doing 1.8 volt from 5 volts is really easy. And the more overhead you have, then the more room you have to do some filtering and cleaning up of power and all that kind of stuff. So all that to say, and again, the input of those LDOs are dependent on the model, but usually in some cases, like they would take the voltage from like a couple domains above, right? So if we have 1.6 volt per domain, the input 2 domains above would be 3.2 volts. And so that LDO would be regulating 3.2 volts down to 1.8. And so this is the same thing for each of them. So that's all fine and dandy, but what happens when you get to the end of the board? So as we know, if we are at the very beginning, so again, if we're in domain 1, and we're looking at regulating 1.8 volt, well, it's easy because we got potentially up to the full board voltage to work with, right? So we got all the way up to 24 volts that we can regulate all the way down to 1.8. Like if I were to take like the input pin of the 1.8 volt LDO there and just connect it all the way to the 24 volts and then change the circuit accordingly, then I could take 24 volts, regulate it down to 1.8, and then I would have like a really strong 1.8 volt that's really, really solid. But as we move up in domains, we know that the voltage increases in steps, right? So, you know, talking about the voltage always relative to your main board negative. So this is the ground of this domain is your main board ground, but as we go up, the ground of each domain goes up by 1.6 volts. So it comes a point where, you know, again, depending on how the board is designed, where you just don't have enough headroom anymore on your board voltage to have enough headroom to generate a strong regulated signal and use enough voltage as an input to your LDO to generate a strong 1.8 volt. So that is why where your boost circuit comes into play. And again, if we said you know, about 2 domains higher, that's 3.2 volts. But if we want, let's say, like a 5 volt, then you would need to be 3 domains over it. So that's why you have your boost circuit. There's a chip usually here, obviously, but that's its purpose. So it's to take your whatever comes out of your Mosfets, your 24 volts or whatever, boosted by a couple more volts, and then use that higher voltage not to feed the chips, because we know the chips are already fed by these traces, which is directly fed by the Mosfets, but that higher voltage is going to be used as a voltage with even more headroom to then go into your LDOs in your last couple domains and be used like that to generate your 1.8 volts and your 0.8 volts for those domains specifically. So when you don't have a boost circuit like this board doesn't have right now, it's missing the chip, it won't change anything except the 1.8 and the 0.8 on the domains that use that higher voltage to regulate it down to generate those voltages. So in the case of this S17 Plus, I believe it's the last three domains. So if I, now without the chip on there, the last three domains should not have a 0.8 or a 1.8 volts, I believe. I've never actually done the test, but I believe that's how it should work. But I'm still going to have all my voltage domains because those are generated by the Mosfets. And I'm going to be able to make sure that my chain works all the way up to my third to last domain. Okay, so that was a high level overview, kind of generic talk about the power distribution on a board. And again, it's somewhat similar for most of the models, but there are some little subtleties here and there. So thanks for listening. Hopefully you learned something. If you got any questions, either come meet me on Discord and ask them, or ask them in the comments, and I'll make sure I get to them. Okay, thanks.